Introduction to Random Variables. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on identifying specific events and calculating the probabilities associated with individual outcomes. Things like the chance of rolling a specific number on a die or getting a certain sequence of heads and tails. However, as we move into more advanced statistics, you'll notice that in many real-world scenarios, we aren't just interested in the outcome itself, but rather a specific numerical value that comes with that outcome. For instance, instead of just looking at a sequence of coin flips, we might want to know the total number of heads we obtained. This shift from looking at qualitative descriptions to looking at numerical data is exactly why the concept of a random variable becomes so essential. It is the bridge that allows us to turn random events into numbers we can actually calculate and analyze. Let's move on to the next slide to see how this works formally. Understanding the concept. At its simplest level, think of a random variable as a translator. In our previous lessons, we dealt with qualitative outcomes, things you can describe with words like heads or tails from a coin toss. A random variable takes those words and translates them into quantitative values, which are just numbers like 1 or 0. It turns descriptions into data. Now, if you are looking at a textbook, you will see a more formal definition. It states that a random variable is a real-valued function whose domain is the sample space, denoted by a capital S, of a random experiment. Don't let the mathematical jargon intimidate you. What this really means is that the random variable is simply a rule. This rule takes every single possible outcome in our sample space and assigns it one, and only one, unique real number. To put this into a mathematical notation you might see in your exams, if we let S represent the sample space and we let X represent our random variable, then for every outcome, which we call S, belonging to the sample space S, the value of X of S is a real number. Now that we've established that we are moving from looking at simple outcomes to looking for numerical values, let's dive deeper into what a random variable actually is. Essentially, we are just creating a bridge between the physical results of an experiment and the world of mathematics. In the next slide, I'm going to show you a step-by-step process on how to actually build this bridge yourself. Step-by-step breakdown of a random variable. Now that we understand that a random variable is essentially a bridge between qualitative outcomes and quantitative numbers, you might be wondering, how do I actually construct one? Well, it isn't just a random guess. There is a very logical 4-step process you can follow every single time. First, you must identify the random experiment. This is simply determining the action you are performing. Are you tossing a coin, rolling a die, or perhaps sampling light bulbs from a batch, as we will see later? You need to know exactly what the event is. Second, once you have your experiment, you need to determine the sample space, which we denote with a capital S. This means you must carefully list every single possible outcome that could occur so that nothing is left out. Third, this is the most crucial part. You must define the rule, which is the actual variable, part of the random variable. Here, you decide which numerical characteristic you are interested in measuring. Are you counting the number of heads? Are you looking at the difference between two values? You are setting the criteria here. And finally, the 4th step is to map outcomes to numbers. Using the rule you just created, you go through your sample space and assign a specific real number to each outcome. If you follow these 4 steps, you'll be able to transform any experiment into a mathematical function. To show you exactly how this works in practice, let's move on to some illustrative examples involving coin tosses. Illustrative examples. Now that we have established the formal definition of a random variable as a rule that maps outcomes to numbers, let's move from theory to practice with some concrete examples. This will help you see how we can apply different rules to the exact same experiment. Let's consider a classic random experiment, tossing a fair coin twice. Before we define our variables, remember that our sample space, which we call S, consists of 4 possible outcomes: heads heads, heads tails, tails heads, and tails tails. For our first example, let's look at example A. Suppose we define a random variable, which we'll call x, to represent the total number of heads obtained in these 2 tosses. Let's apply our rule to each outcome. If we get the outcome heads heads, we count 2 heads, so x of heads heads equals 2. If we get heads tails, we have just 1 head, so x of heads tails equals 1. Similarly, for the outcome tails heads, we also have 1 head, meaning x of tails heads equals 1. Finally, if we get tails tails, there are 0 heads, so x of tails tails equals 0. Notice what happened here. The random variable x has taken our qualitative outcomes and mapped them to a specific set of numerical values, specifically, the set containing 0, 1, and 2. Now, this is the important part. We can use the exact same experiment but define a completely different rule. Let's look at example B. Suppose we define a different random variable, let's call it y, to represent the difference between the number of heads and the number of tails. Let's trace this rule through our outcomes again. For the outcome heads heads, we have 2 heads and 0 tails, so y of heads heads equals 2 minus 0, which is 2. For the outcome heads tails, we have 1 head and 1 tail, so y of heads tails equals 1 minus 1, which results in 0. For the outcome tails heads, we again have 1 head and 1 tail, so y of tails heads equals 1 minus 1, which is also 0. Lastly, for the outcome tails tails, we have 0 heads and 2 tails, so y of our tails tails outcome equals 0 minus 2, which gives us negative 2. In this second case, our random variable y maps that same sample space S to a different set of values, the set containing negative 2, 0, and 2. As you can see, the experiment hasn't changed, but by changing our rule or our random variable, we get entirely different numerical data to work with. This flexibility is exactly what allows us to perform the complex statistical analysis we will see in our next slide regarding real-world applications. Real-world application. Now that we have seen how we can apply different rules to a simple coin toss, let's step away from games of chance and look at a more practical, real-world application. Imagine you are a quality control engineer working in a factory. Your job is to inspect a batch of 3 light bulbs to check if they are defective, which we will label with the letter D, or non-defective, which we will label with the letter N. Before we can assign any numbers, we first need to identify our sample space, which we denote as capital S just like we did with the coin tosses in the previous slide. We must list every possible combination of 3 bulbs. So, our sample space includes outcomes like NNN, where all are good, NND, where only the last one is bad, and so on, all the way to DDD, where every bulb is defective. In total, we have 8 possible outcomes in our set. Now, here is the crucial part where we introduce the random variable. Instead of just looking at these letters, the engineer wants to measure something specific. They are interested in the total number of defective bulbs found in the batch. We will define this specific rule as our random variable, and we'll call it capital Z. Let's look at how this variable maps our outcomes to actual numbers. If the outcome is NNN, there are 0 defects, so Z of NNN equals 0. If we have outcomes like NND or NDN or DNN, each of these contains exactly 1 defective bulb, so Z of those outcomes all equal 1. If we see 2 defects, such as in NDD, DND, or DDN, then Z equals 2. And finally, if the outcome is DDD, then Z equals 3. As you can see, by using the random variable Z, we have successfully transformed a list of complex letter combinations into a simple set of numbers: 0, 1, 2, and 3. This is incredibly powerful because, as we will see in the next few slides, it allows the engineer to move beyond just listing outcomes and actually perform mathematical calculations, such as calculating the average number of defects per batch. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. As you begin working through more complex probability problems, you might encounter these 3 specific mistakes, so let's make sure we address them now. First, be careful not to confuse the outcome with the value itself. This is a very frequent error. It is easy to look at an outcome, like heads followed by tails, which we write as HT, and think that this outcome is the random variable. But remember what we discussed in the earlier slides. HT is simply an element of our sample space. The random variable is actually the mathematical function that takes that outcome and assigns it a number. For instance, if our rule is to count the number of heads, then x of HT equals 1. The outcome is the input, and the random variable is the rule that gives us the numerical output. Second, try not to assume that a single experiment can only have one random variable. It is a common misconception to think that once we define a variable, we are done. However, as we saw in our coin-tossing example with variables x and y, the same experiment can be analyzed in multiple ways. Depending on what specific characteristic you choose to measure, whether it's the total number of heads or the difference between heads and tails, you can define entirely different random variables for the exact same sample space. Finally, never ignore the domain. When you are defining a random variable, you must ensure that every single possible outcome in your sample space is assigned a value. A random variable is only complete if it is defined for all s, where s is an element of the sample space S. If you leave even one outcome without a numerical assignment, your function is incomplete. Keep these points in mind as we move into our final summary of the key takeaways. Key takeaways. First and foremost, remember that a random variable is not just a number, but a function. It is a rule that takes the outcomes of a random experiment, those qualitative results we discussed earlier, and maps them directly to real numbers. Second, keep in mind the mathematical structure we've used. The domain of our random variable is always the sample space, which we denote as capital S. This means every single possible outcome in our sample space must be accounted for. Third, notice that the range, or the set of actual values we get, isn't fixed for every experiment. It depends entirely on the specific rule or the variable you define. As we saw with our coin-tossing examples, one rule might give us values like 0, 1, and 2, while a different rule could give us negative values. Finally, the real power of this concept lies in its ability to transform qualitative data, things like heads or defective, into quantitative data, which are simply numbers. By converting outcomes into numbers, we move away from just describing what happened and move toward being able to perform much more complex and meaningful statistical analysis, such as calculating averages or predicting future trends. All right, we have reached the end of this lesson, so let's take a moment to wrap everything up and consolidate what we have learned today. That concludes our introduction. Great job following along today.